Welcome to HB Tuner's GM Gen 4 Training Part 42. This training module, we're going to take a look at working with our switching voltages in our closed loop fuel correction. So this is going to be how the voltage is interpreted from the engine control module, from the actual primary oxygen sensor, which drives the closed loop behavior. We're going to learn how we can work with this and how we can change our switching voltages to get our air fuel back in line if we're running richer or leaner than our desired target at idle and cruise conditions. We're going to have a lot to cover. Let's jump in so we can check this out. Okay, so let's get started. We're going to be taking a look at working with our switching voltages in our closed loop operation for our Gen 4 vehicles. Our switching voltages are going to be driving what the closed loop behavior is going to do. It's essentially reporting back how far our fuel mixture is off in our exhaust stream. So it actually is going to be reporting how much oxygen content is in our exhaust stream back into the engine control module, and based on having more or less oxygen, based on what that sensor signal is outputting to the engine control module, it then drives the closed loop behavior. So it's either going to be adding or subtracting fuel to the injector pulse width calculated from our airflow model. And we'll find the switching voltages are the main driving factor in telling the engine control module where stoichiometric is going to happen at. So if we install a set of long tube headers, things are going to be thrown off. In this situation, we readjust our switching voltages so that if we're looking at a wideband display, it's going to be reading more like 14.7 or 1.0 lambda on that wideband display at idle and part throttle rather than being at, let's say, 13.8 or 15.6 air fuel on that wideband display, or something like 97 to 1.03, 1.04 lambda. It's going to be tracking more like 1.0 lambda or 14.7 to 1. That's our stoichiometric point, and that's what we want to go after in our closed loop behavior. Now we can influence this and actually have the closed loop start to look at a switching voltages that's slightly off-center from that, meaning we can actually bias in closed loop. So wherever fuel trim's running, they can actually start to try to bias and chase after a leaner mixture. So we can go after economy. Maybe want to shoot for something like 15.2, 15.5 to 1 air fuel, or something like 1.03, 1.04 lambda. We could actually get a little bit of economy like that and still have the closed loop run and be accurate. Or if we're finding that for some reason we want to run slightly richer, maybe we have a big set of injectors that don't run real linear, when we want to go and richen up our target mixture under closed loop, so at idle part throttle it drives a little bit smoother, we stretch out the injector pulse a little bit, put it in more of a linear operation mode or zone, we could go and do that with the switching voltages. So we have the authority to probably move our air fuel reference in terms of what it's shooting for and trying to go after in those switching voltages, which relate to an air fuel reading, and we'll get into that here in the VCM scanner in a little bit. We have the ability to offset and influence what our air fuel is going to be doing in referencing in closed loop by probably about a point. So we could probably go down to the maybe mid to low 13s or go up to high 15 to 1 air fuel when closed loop is running. This is going to be essentially a hack or a trick that we can manipulate the closed loop behavior to do what we want. Or if we put a set of long tube headers on, we space our oxygen sensors further downstream, there is going to be more of a air built into the oxygen sensor reading, because the switching voltages and the oxygen sensor behavior is all built off the factory locations when we're talking about how this all functions. If we move the oxygen sensors further downstream, that throws off that calibration. So naturally, we'd have to go in and adjust our switching voltages. So that's what we're going to be going and talking about here, how to adjust our switching voltages for the situation if we have a set of long tube headers installed. Let's jump in here and take a look at where we can find our switching voltages. And then I'm going to talk about how this fits in to the different airflow modes within the switching voltages. Then we'll talk about how we can move into the VCM scanner and determine how and if we need to adjust the switching voltages. You may not have to. I've had plenty of cars with long tube headers that I've just left all the switching voltages alone and everything was tracking properly for the fueling, but I have had some vehicles where I had to go in and change it. That was a necessity in order to get things back in line. Let's go take a look at this. Now I have a Cadillac CTSV example file open here. Any Gen 4 calibration file will work, so it doesn't matter what we're looking at in terms of the Gen 4 files. The switching voltages references are all going to be the same and how it works. Let's jump in here into our engine tab, and we're going to go from our general tab over into our fuel, and under fuel here we're going to move into oxygen sensors. Now under oxygen sensors we have a couple areas we want to take a look at. We want to be looking at our mode versus airflow. This is going to be establishing what specific airflow mode we're looking at or operating in to reference our switching voltage table here. And we also have a upper and lower O2 limit that we'll discuss here very briefly. But what we're going to find here is that these actually 3 tables here, our mode versus airflow and our upper and lower limit, are the tables that we might need to adjust if we need to get into adjusting and changing our switching voltages. So let's actually break down how this works. If we jump in here to our switching voltage table, we're going to find that we have values that are headers to the tables of 0, 8, 16, 24, 32, 40, 48, 56, and 64. The values in the table themselves, these are going to be in units of millivolts. The primary oxygen sensors are a 0 to 1 volt narrow band, or 0 to 1000 millivolt narrow band type signal, where at approximately 450 to 500 millivolts, what we're finding here, that signifies where stoichiometric operation is going to be in terms of the sensor's output. So again, it has that 0 to 1000 millivolt or 0 to 1 volt output relative to how much oxygen content is in the exhaust stream. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.